Hello Math 3410 students, let us go over exam 1. Exam 1 problem set consists of 3 problems with some multiple parts. Number 1, a separable equation. Number 2, a first order linear differential equation. And finally number 3, a second order linear differential equation. Let's begin with number 1, a separable equation. It looks like this. And please note that this is separable. How can you tell? Here, do you see any t expression? No? A and b are constants. P is the function, no t. So this is separable. You can divide the entire thing to the left-hand side and right-hand side just dt. So we have a separation. And once you have the separation, and then you can integrate and solve for p. And finally, once you have the solution, you can put in this initial value condition. IVC. Let me expand the font so that I can read this better. Okay, IVC, P of 0 is B over 2. And then once that is done, you can do this. P of t goes to B as t goes to infinity. Let's talk about all these. The first step is to solve this general solution. And the first step of the first step is the separation. Here we go. From here, we can divide away the p parts, and then we can get this separation. Now, it is possible to get a little bit different separation, if you will. For example, if you leave the entire fraction a over b in the right-hand side, and then get this form, and that's fine. And if you want everything here and then leave nothing in the right-hand side, that's fine too if you want. My decision is to keep A in the right-hand side and B move to the left-hand side. Why did I do that? This yields just a little bit simpler computation in step 3. Not step 3, excuse me, a couple of lines later, excuse me. Okay, now that we have the separation, let's take the antiderivative of both. How to take the antiderivative of the right-hand side? That's easy. Left-hand side, that's going to be a bit of a problem. And what technique do we use? We use partial fraction. That's why I had this b here. The partial fraction is simpler this way. But if we didn't have it, if this had been just 1 and this had been just a over b, then this would have been a over b. And this way here we can get 1 over b. And then b's cancel each other out now. And then we have the same thing. So it doesn't really matter what you do here. Still, a little bit simpler way is to keep b on the left-hand side, and that's why I kept this way. Now, as for this partial fraction, this should not cause any kind of trouble to anybody. Anybody who had some reasonable success in Calculus 2 should be able to do this to that partial fraction without any kind of trouble whatsoever. In this class, we did so many different types of partial fractions, including some really horrendous computation that we has to rely upon computer algebra system. This is not one of them. This is one of the easier one, especially considering that denominator was already given in a factored form. So don't complain. This is something you have to do, and that's within my expectation. Now let's go over to the next step. Take the antiderivatives. We have logarithm minus logarithm here. Please note that this plus became this minus here, and that's because of the chain rule. You see this minus is generating this minus. That's coming from the chain rule. The detail is left to the students. Okay, now here's an interesting part. My way is to solve for p here using algebraic method, and the motivation for that method is almost entirely outside mathematics, because that way I can get the general expression of p so that I can use it to explain what kind of model this one is and how is it related to population dynamics or epidemiology, or how rumors spread out in social media, and so on and so forth. But in this class, in this exam, there were many students who did it in alternative fashion. As a matter of fact, let's see, including the student who got 100, and then the student got 90 or higher, and then let's see, there was a couple of students got 85 or higher. Yeah, all those students did it this way. They plugged in the numbers right here. When t is equal to 0, p is b over 2. So plug in the number right here. Yes, you can do that because you just took the antiderivative. And then that's when t is equal to 0. So plugging in the numbers right here, right away, you can get this equation. And then you can find out what c is. This is 0, so I don't have to worry about it. And then this part is going to be your c value, but if you simplify, what do you get? Log of b over 2 minus another log of b over 2, that gives you c equals to 0. So this part is just 0, and then go back and work out. You're going to get your p in a little bit more explicit form, but implicit form is acceptable. So this is what most people did in this class, or actually everybody who earns full credit did this way. Still, let me do it my way, and I already gave you the motivation. It is mostly for application. Okay, let's go. How do you do that? Look at the left-hand side. We have log minus log, so we can use log rule to combine those into a single logarithm, log of fraction. And then you can remove the logarithm altogether by taking exponential of both sides. So log is gone, but right-hand side we have an exponential. Now let's simplify this. This is rather typical technique. Plus c in the numerator, plus in the power, we can decompose by the same base and e to the c power. So c is arbitrary constant that can be identified through the initial value condition. We have e to the c power, so we get arbitrary positive constant that will be identified later. It's a little bit convenient this way. Okay, all right. And then let's do one further simplification. We can remove the absolute value by putting plus or minus. And by putting plus or minus, this arbitrary positive constant c is positive because it came from exponential. So we have this positive. Now plus minus positive, so this k can be negative. So what did you end up with? Arbitrary constant k that will be determined later through IVP. So initial value condition here, put in appropriately and solve it, and you're going to get k value. So it doesn't matter which character you use and what you do, it's going to be determined later anyway. So far so good, and let's work out this algebraic equation to find out p. How do you do that? It's a linear fractional equation, so let's follow the standard process. Number 1 is the denominator. Multiply out the denominator to the other side. Number 2, break out the parentheses. Distribute the exponential, and then we can break out the parentheses. And what do you get? We have p here, and then another p term here. So put those together. All the p terms on the left-hand side, and no p in the right-hand side. All p here, no p's there. And then if you factor p out, you have the solution. You can divide away this part, and then what do you get? We get this linear fractional equation, linear fractional function, and that is your p. In this notebook, I did just a little bit more simplification, and again, the motivation for this simplification is more toward the modeling in biology and social science and so on, rather than mathematics itself. In any case, we can simplify like this by dividing away these exponentials, and 1 over capital K, let me rewrite it as small k, and we have the final form. P of t is b over 1 plus k times e to the negative at. And that function is actually an important class of function called logistic function. And that is a solution. That is the solution of this kind of system. We'll talk about the relationship between one and the other in a separate video. For now, let's finish the problem. We have this general expression. So let's apply the initial value condition to this general expression, which I have over here, and plug in t equal to 0. What do you get? P of 0 is b over 2, so that's the right-hand side. And t is equal to 0, so this is 0. We end up with e to the 0 power. What is e to the 0 power? It's 1. Therefore, what do you get? b over 1 plus k is equal to b over 2. We can solve this with respect to k. K will turn out to be 1. That generates the final answer of this problem. P of t is b over 1 plus e to the negative at power. Once we have that, or in general, over here even, we can calculate the limit. It's not difficult at all. Basically, we have e to the negative infinity power. So you see e to the negative at power, a is positive, so e to the negative infinity power. E to the negative infinite power is 0, so k times 0 is also 0. All this part drops out. All this part drops out. What do you get? We have b over 1. That's b, and that is the proof. There are other proofs, yes, and there are other ways that some students earn full credit, but this is the most explicit. By the way, let me show you some pictures here. This is a graph of the solution function. P of t is equal to b over 1 plus k e to the negative at power, where a, b, and k values are given as follows. A is 1, b is 1, k is also 1. And as you can see, this is related to population dynamics, and you can see that grows relatively slowly here and explodes, and then later on growth slows down to mature population later on. Let's see how these parameters affect this number. If I change into higher number, a is becoming higher, then what do you get? Oh, growth is more quick. So if this is an epidemic model, bigger A means faster spread. And how about B value? Let's change it to something bigger, like 10 instead of 1. Any change? No change? If you look at the shape of the graph, you won't see any change, but look at this labeling. Used to be 1, now mature population is 10 units. Let's go back to 1. See, no change in terms of shape, but labeling changed. So that is the mature population. K value is related to initial value. Changes to something 3, then as you can see, you have a little bit smaller initial value. And then if you take something smaller than 1, then you're going to get higher population, higher initial value, higher initial population. Okay, that completed problem 1A, and along with some visualization, I guess let's do problem 1B in a separate video.